All right, so there is a theorem about the test for increasing and decreasing functions. I think it's called Theorem 3.5. This is not like geometry where I ask you to cite the specific theorem. But that particular theorem says that if f is a continuous function on the closed interval and it's differentiable on the open interval. Okay, I'm not worried about whether it's differentiable at the endpoints. I could have vertical tangents at the endpoints. So that's why we exclude the endpoints. But it's continuous on the closed interval, differentiable on the open interval. We've seen that qualification already before, and we'll see it again. First of all, if the first derivative is greater than 0, then f is increasing.
Is f a constant?
It's a function. F's your function.
I'm saying, what does that say? F is a...
If f prime of x is greater than 0,
No.
oh, if f is continuous. I'm sorry, I should have left off the a. Thank you, Molly. Okay, if the first derivative is greater than 0, then f is increasing on the interval. If f prime of x is less than 0 for all x in the interval, then f is decreasing on the closed interval. And then if it equals to 0, if the derivative equals to 0, then it's a constant function.
What is that? F is INC? What is that?
Increasing. All right, so we're going to use this theorem to help us determine intervals that a function is increasing and decreasing. Where can a function change from increasing to decreasing? Hunter? Okay, when the derivative changes from 0, right? That's where it's going to happen, or where it's not differentiable. In other words, what did we call those points where that happens? Critical numbers. Turning points. The only places things can turn is at critical numbers. Okay? They don't always have to turn at a critical number, but that's the places that they can turn. So let's look at a function. F of x equals x times the square root of 16 minus x squared. And we want to do this without our calculator. Okay. We want to determine the intervals where this function is increasing or decreasing. And the first thing I need to look at is domain. What is the domain of this function? Where would we look to see if we have restrictions?
Asymptotes?
Any denominators in where we would see asymptotes? Do I have any denominator? No. Where else do I have to look for the restrictions?
Powers?
Under the radicals. So what's underneath the radical has to be greater than or equal to 0. So 16 minus x squared has to be greater than or equal to 0. So we did this last year. So there either have to be, I think what we did last year, remember we did our number lines? And we looked for where things would be. If we have negative 4 here and positive 4 here, if I choose, say, a 0 to plug in to both of those, do I get a positive number or a negative number? Okay, so if I choose 0, that's going to be over here is positive. And here's positive. Okay, what if I choose something that's less than -4? If I choose something that's less than -4, you're going to get a negative. What if I choose something that's greater than 4? I get a negative. So where is this greater than or equal to 0? Between -4 and 4, so that's my domain. You also might remember that just that part of this equation, if we only had square root of 16 minus x squared, that's the upper part of a circle whose radius is 4. And so the domain is -4 to 4. If you remember that, that saves you time. All right, so our domain is -4 to 4. We want to determine where's it increasing, where's the function decreasing, and we determine that from the first derivative. So I need to figure out, if I want intervals where it's increasing or decreasing, I need to find out where it's going to change, and that's going to occur at critical numbers. So first step is find our derivative. And this is the same as x times 16 minus x squared to the 1/2. So we have to use product rule. You cannot distribute that x inside the square root. Well, it'll be the product rule and the chain rule. Okay, so the first term times the derivative of the second. Okay, to the -1/2 times -2x. Plus the second term times the derivative of the first, which is just 1. Right, I can simplify a little bit. 1/2 and 2 cancel. So we have -x squared times 16 minus x squared to the -1/2. Plus 16 minus x squared to the 1/2. Now I am going to, well, I want to get rid of that. Factor out the common factor, and that's the lowest exponent. So it's, I'm going to, pardon? We will in a minute when I simplify it. So we're going to take out a 16 minus x squared to the -1/2, and I'm left with -x squared plus 16 minus x squared. And so the derivative equals 16 minus 2x squared over the square root of 16 minus x squared. That's f prime of x.
How'd you get 2x squared? She just added those. Oh, those are being added, not multiplied. Okay, my bad.
All right, now I know a lot of you would prefer to rewrite this as a fraction and then get a common denominator, and sometimes that's okay. But doing it this way, as we go on, is a lot of times going to be simpler when you combine over here. So it's really easier in the long run to factor out the lowest exponent. All right, so here's my derivative. I need to find my critical numbers, and critical numbers occur where? Where the derivative is 0 or does not exist on the interval. All right, so where is this derivative going to be equal to 0? I only worry about, if I'm finding where it's equal to 0, I'm only worried about the numerator. Well, let's see. We get 2x squared.
Wait, why not the denominator?
We'll get to the denominator in a minute. That's where it doesn't exist. So x squared is 8. So x equals plus or minus 2 square roots of 2. These are critical numbers. Where does the derivative not exist?
The denominator, so like 4 and negative.
Okay, so it does not exist at 4 and negative 4, but what's our range here, our domain? Negative 4 to 4. So what does that mean, do you think, about what's happening to the graph at negative 4 to 4? What kind of tangent will I have there? We'll have what kind? Vertical asymptotes at the endpoints of our interval. And we'll look at this in a minute and see if that's really what's happening. But we have vertical asymptotes at the endpoints of our interval because it's not differentiable at the endpoints. That's why endpoints are excluded from our theorems and definitions. All right, so let's see how we can determine where we're increasing and where we're decreasing. Going to move this out of the way. Our critical numbers then are plus or minus 2 square roots of 2. We're going to set up intervals to check. It's kind of like what we did last year when we looked at inequalities, quadratic inequalities. But we know we're going to start at negative 4. And we're going to go to negative 2 square roots of 2. That's one interval. And then we have an interval from negative 2 square roots of 2 to positive 2 square roots of 2. And then we have an interval from 2 square roots of 2 to 4. Those are the only places where the derivative is 0 or does not exist, so it's the only place where we could possibly change from increasing to decreasing, where you have a critical number. Make sense? All right. So what we're going to do, and I don't really care what the value is, I just want to know negative or positive. So I'm going to choose some value of the derivative that's in that interval. So what's some number between, I think we could use negative 3, f prime and negative 3. I don't care what it is, I just want to know, is it negative or positive?
You plug it back into...
Plug it back into the derivative, and really here all we have to worry about is the numerator, because the denominator is going to always be positive.
Plug it in the
Numerator. So if I plug in a negative 3 in the numerator, it's going to be less than 0. So this means we are decreasing here. I don't care what it is, I just need to know is it negative or positive. I don't need the value. Okay, here in this interval, the easiest one to choose is 0. If you can use 0, always use 0. If I plug 0 into my first derivative, it's going to be positive. So what does that tell us about the function? It's increasing. And then if I choose f prime, say f prime of 3, it's going to be less than 0, so that means that we are going to be decreasing. So if we want to list our intervals where we're increasing and decreasing, I'm going to move this out of the way. I want to show you how I like to list it because it's very helpful. We are decreasing from negative 4 to negative 2 square roots of 2, and from 2 square roots of 2 to 4. And we are increasing from negative 2 square roots of 2 to 2 square roots of 2. Let's change at negative 2 square roots of 2 and at 2 square roots of 2. I think it'll be helpful if you do, because now if we want to figure out where our maximums and minimums, what those values are, we're going from decreasing to increasing. Is it going to be a minimum or a maximum? going from decreasing, which means it's going like this, to increasing. Is it going to, if we're going from decreasing to increasing, it's going to be a minimum. All right, so if we're going from decreasing to increasing, we have a minimum when x is negative 2 square roots of 2. We can plug that back into the equation in a minute to figure out what the value is. What happens when you go from increasing to decreasing? We have a maximum at 2 square roots of 2. So that's why I list them this way, because I can see, helps me see, I can think through it, what's happening. And so now, if we go back in, and I've lost my original equation because I pushed it off, it is f of x equals x times the square root of 16 minus x squared. Just to save time, would you believe me if I tell you that the point here is, it's a minimum, I believe it was negative 8, because we're going to have 16 minus 8, which is the square root of 8, and the square root of 8 times the square root of 8, negative square root of 8 is negative 8.
Wait, so do you just plug it
Back into the original to find the actual minimum and maximum. And what I just demonstrated was the first derivative test. The first derivative test. So let's look at what the first derivative test.
I'll be right back. So fast.
Do what? Okay, go ahead. Let me see if I can get some of this out of the way.
You writing a book? I said you writing a book?
All right. Okay, we're going to talk about the first derivative test, which we'll use a lot. Matt. I'm trying to talk. All right, if C is a critical number of a function, then I'm going to abbreviate Cn. C is a critical number of a function that's continuous. If the function is differentiable, except possibly at C. Because if it's a critical number, it could be that it's not differentiable at C. Okay, but everywhere, if it's differentiable everywhere else, then by the first derivative test, if f prime of x changes from negative to positive at C, then f of C is a relative min. If f prime of C, or x, changes from positive to negative, at C, then f prime, and then f of C is a max. And if you just think about it, if you go from negative to positive, you have a minimum. If you go from positive to negative, you have a maximum. And if it does not change, if f prime of C does not change, or f prime of x does not change at C, then it is not an extrema. F of C is not an extreme. Did I say it wrong? If f prime of x changes from, yes, at C. So that is our first derivative test. Yes?
Is there a difference between relative and just, yeah, I was gonna,
All right, let's look at f of x equals x cubed. I want to determine here, do I have any extrema? Is this an increasing function or a decreasing function? You could probably tell me that right now. You should know what that looks like, but let's go through the process. To determine intervals, first of all, are any restrictions on the domain? No, no restrictions. So my domain is negative infinity to positive infinity.
How do you determine the domain?
This is a polynomial function, and a polynomial function always has a domain of negative infinity to positive infinity.
So is this basically kind of a longer way to find extrema, or?
Yes.
Okay, it's not a longer way.
That is the way.
It is the way. The problem we chose, that last problem was just a little bit longer to find the derivative. Okay. Yes.
Okay, so since it's not a closed interval, they're just going to be relative, right?
Yes, if there are any.
So it's like doing what we did before, except we have to find the interval ourselves.
Yes, now we have to find the intervals. All right, so let's think about this. What's the derivative?
3x squared.
3x squared. What's the critical points or critical numbers? Molly. Okay, critical numbers. X equals 0. Everybody all right with that?
Did you just,
So I'm going to check from negative infinity to 0, and from 0 to infinity. If I check f prime at 1, negative or positive? Positive. I mean negative 1. If I check f prime at 1,
wait, that was,
f prime at negative 1 is going to be,
that, if it was negative 1, wouldn't it not mean?
what's the derivative?
Oh, we used the derivative. How do we know when to use what?
If you're checking for increasing or decreasing functions, critical numbers, you use a derivative. What about f prime of 1? It's positive. All right. So what does that tell us about this function?
It's a,
It's just always increasing.
Always increasing.
oh, wait.
It's always increasing on its domain. So negative infinity to positive infinity, it's increasing.
So is that it?
On this particular function, because it's increasing, it has no extrema.
How'd you get the critical number to be 0?
Set the derivative equal to 0.
And that gets you 0?
That's, yeah.
Okay.
All right, we say that this function is strictly monotonic.
The pentatonics.
Monotonic, not 5, 1.
I left my dictionary upstairs.
That's what I call it.
And does Todd give to
I am strictly monotonic.
No, it's strictly monotonic. It simply means it's always increasing, or always decreasing, or always constant.
dead mouse?
Strictly monotonic. Mono, it's not going to change. Always increasing, always decreasing, or always constant. So while this function looks like this, it's strictly monotonic. If I had Right, never changes. This function is not strictly monotonic because it goes from increasing to constant to increasing. So that's a term you're going to see. And I wanted to give you an example. So it just means it's either always increasing, always decreasing, or always constant, strictly monotonic. Yes, sir?
How do you determine that point? Negative infinity, point zero, point infinity.
Critical number. The critical number was? You told me what it was. Yes, you did. F prime of x is 3x squared. You told me the critical number was 0. Yes. All right, let's look at another problem.
Why is this one have to be hard?
It's not hard.
There's a fraction.
Oh my gosh. A fraction?
Oh my god. Fractions.
Okay, I want to find the extrema in the interval from 0 to 2 pi. You can do that. What's the first step? Find the derivative. Paul, what's the derivative?
Well, it looks like we're gonna have a 1/2 minus cosine x.
1/2 minus cosine x is our derivative. Now I have to find critical numbers. Where does the derivative equal 0?
Right.
Okay, so the cosine of x equals 1/2 at pi over 3 and 5 pi over 3. It's probably in the book. No, he knows his unit circle. Praise the Lord. I'm glad somebody knows their unit circle. Okay, so we've got intervals to check. Remember we said we were going from 0 to 2 pi. Cosine is only positive in the first and the fourth quadrant, which is why it is pi over 3 and 5 pi over 3. All right, so we're going to check from 0 to pi over 3, from pi over 3 to 5 pi over 3, and from 5 pi over 3 to 2 pi. Okay, what you're doing now is finding critical numbers, which is helpful on the quiz.
What is the quiz about? Just critical numbers or?
Critical numbers and absolute extremes.
Okay, I mean, you wrote critical numbers by like pi over 3 and 5 pi over 3.
What?
So aren't we finding the critical numbers?
Okay, those are the critical numbers. These are the intervals that we're going to check.
Okay, so this is relative, but on the quiz will be absolute.
Applies to absolute also?
Except you have endpoints. You don't have to find where it's increasing and decreasing if it's absolutes. All right, so we're going to check the first derivative. What's something that's that's between 0 and pi over 3? Pi over 6. You don't know what the cosine of 1 is. So the cosine of, if we plug into our derivative, what's the cosine of pi over 6? Shh.
Is this over 6 or is this over 3?
This one is? So the square root of 3 over 2.
Square root of 3 over 2. So 1/2 minus the square root of 3 over 2. Negative or positive? Negative. Okay, I'm just going to, between pi over 3 and 5 pi over 3, we can do pi over 2. What's the cosine of pi over 2? 0. So 1/2 minus 0 is positive. All right, and between 5 pi over 3 and 2 pi, 11 pi over 6. And the cosine of 11 pi over 6 is Not negative. Square root of 3 over 2. 1/2 minus the square root of 2. Negative or positive? Okay. So let's think about our intervals. Chin.
What about the 0 to 2 pi?
Here's 0, and here's 2 pi. All right, so we are decreasing from 0 to pi over 3. I am increasing from pi over 3 to 5 pi over 3. And then I am decreasing again from 5 pi over 3 to 2 pi. Okay, so that tells me where I'm increasing and decreasing. It changes at pi over 3. So when x is pi over 3, do I have a minimum or a maximum? Minimum. What happens when x is 5 pi over 3? We have a maximum. Okay, now if we go back to our original equation, which was 1/2 x minus the sine of x.
I don't think there's a. So we don't do the derivative. I can't get this.
To find the actual point, you go back to the original equation. All right, so we're going to have pi over 6. Hang on, let me look at this one quickly, and then we will go, I'll give you your assignment. Because I just want to talk real quick about what happens when you have a break in the graph. What's going to happen in our graph when x equals 0?
Error.
Error, which means we're going to have a vertical asymptote. Okay. X equals 0 is not in our domain, so we have to consider that when we set up our intervals. Yes. Okay, so let's see how that's going to work. If I simplify f of x, this becomes x squared plus 1 over x squared, right? Yes. All right, so if we take the derivative, we get 2x minus 2 over x cubed. Is that right? And so if you wanted to, you could go ahead and put it all together, get a common denominator. I'm going to have to multiply the top. This is going to be 2x to the 4th minus 2 over x cubed. There's my derivative. You can get that as well from the quotient rule. So let's think about what my critical numbers are. We set the numerator equal to 0. So 2x to the 4th equals 2. X to the 4th equals 1. So what is x? Plus or minus 1. All right, so your intervals, and that's all we're going to talk about right now is just the intervals. The intervals are going to go from negative infinity to negative 1. From negative 1 to 0. And I usually draw a line to remind me I have an asymptote there. And then we're going to go from 0 to 1 and 1 to infinity. So you can check those intervals.
So there's an asymptote. Wait, is there an asymptote at all? Every interval since it's the.
No.
It's the open.
No. Because our original function said x can't be 0.
Okay.
That's why.
Oh, okay.
So you have to look at restrictions on your original domain. And there's an asymptote when x equals 0 on our original function. So that's why I drew a line between. Because over here, I'm either going to have one minimum or one maximum.
Okay.
Over here, on this side, it's either a minimum or a max. 1. over here is a minimum or a max. It's not going to be a minimum or a max when x is 0. Because there's a
Okay,
break
so
in the
those,
graph.
okay, so those intervals basically like just represent everything except where the derivative equals 0. Because since it's like
Well,
closed
this
there,
is where the derivative equals
but
0.
since it's open, it doesn't like represent it, right? Because it wouldn't include -1, it would just kind of be there.
Yeah, we're looking for the intervals because at x equals -1, the derivative equals 0. So it's only increasing or decreasing from negative infinity to
So
negative
it's kind of like,
1.
it's like approaching and then like.
Yes, yes. Okay. Assignment. How do you find what? Same way we did before. For time's sake, I'm not going to go through it. I'm just warning you about when you have a break in the domain.
So you could all, like, even if it didn't say x is not equal to 0, you could just tell by the original function that 0.
Yes. All right, there's your assignments.